So that's the topic for today is NA, especially I think NA. Um, and so I think most of you already saw this. So I'm a psychologist, a professor at University of São Francisco in Campinas, Brazil. So I have a program in psychological assessment. Now I'm a visiting scholar at Berkeley and probably will continue on Lehman Center. That's really exciting to join the Lehman Center the second half of this year. And my area of study is psychometrics, intelligence, and now I study a lot social emotional skills and it's psychometrics and assessment. Um, so the topic for today is based on I had like a grant from CAPES from 2006 and 2011 to study the validity of ENAD, especially ENAD and then for assessing the quality of course in higher education in Brazil. So the idea was to evaluate the if the inferences that we do and the actions that we think about based on these scores are if there is like theoretical and empirical evidence to justify the interpretation we do about the scores, about the inferences we do from these results. This is the concept of validity. Okay, so how valid are the interpretations we do about the results of these tests? And with this project, we did a lot of psychometric analysis of NA and ENAD, like the item factor analysis, criterion validity studies, like testing how related, for instance, NA is to ENAD later. We also thought about developing, proposing different ways to interpret the results. And from that, so we had 4 dissertations and 4 master theses in this period, with this kind of more basic validity questions for this tests, right? So the topics for today, I thought we could like go and so the first one is scoring ENEM, and so here there is a lot of implications for especially public policy implications. I don't have, I probably not have time to discuss ENAD today, so unfortunately, but I will keep this for a maybe a new session in the next semester, but the next fall. So because there's a lot of things to see in this NA, so I don't think we'll have time to go over all the others. But anyway, so just a little bit of background on NA. So there's almost 6 million students in Brazil doing NA, is equivalent of SAT, and is used for selection in various universities in Brazil. Now it's composed of 4 multiple choice tests of 45 items each in these areas like human science, natural science and technology, language, and math. And it uses IRT to score, right? And we call 3-parameter model. We'll discuss in a little bit what it is. So this model characterizes each item considering their difficulty, their discrimination, and the guessing parameter we call. So these are the 3 parameters of each item. So what I will discuss is what is the logic behind this scoring. We will discuss a little bit about this optimum scoring weights. The assumption of unidimensionality is a very important part of validity of this engine of scoring. The question is there evidence of secondary factors or second dimensions on the data? If it's true, what is the implication for the scoring? And then I will try to propose that we should change the scoring engine from 3 parameter to 2 and 1. And then I have this what? Because usually there is a fight between people that advocates of 1 parameter rash models and 3-parameter models. There is this fight in the field, and it's kind of a religion that we should use this one. So that's, and usually most of these like large scales assessments using 3-parameter model, and they have like this fight saying, no, we will lose a lot of information going to other models like 2. And I will show you why I think it would be a good idea to change to 1 or 2-parameter model. So what is IRT and how does it score test items? So IRT is a model, right? It's a statistical model trying to predict the outcome. Like it's a theory, it's a mathematical model of the situation, like a student answering a test and giving you the right answer. So the outcome of this situation is if he gets or not the right answer, like 0 or 1. And the this model takes into account the person and the item, the interaction between the two, and what happens if it tries to predict this 0-1 outcome. And it considers the ability, of course, the person, the difficulty of the item, plus some other characteristics like discrimination, guessing, right? So the 3-parameter model has these forms of like, we have like the ability of the person, and B is the difficulty of the item. If the ability is higher than the difficulty, it predicts that it will be much more likely to 1 occur than 0, right? And but also considering discrimination and guessing parameters. So this is the general idea of the model. And this is modeling each item of the test and each interaction between the person and the item. Of course, a person has one quantity that is his ability, and the item has these 3 quantities, 3 parameters that are their features. Like, so this is the 2 formulas. I will not go into detail, but this is formula for 1 parameter, and this is the formula for the 3 parameter. Here is the function that expresses this model, the relationship between the probability of getting the correct answer. So that is a continuous variable. Like, of course, either person gets the item right or wrong, but what we model is the probability of getting it right. And so it's a continuous variable. And then you have the latent traits, the ability, the proficiency. And then this is the function, like as a logistic function, right? That as higher as the ability, the higher the probability that the person gets it right, the item right. This number here is the guessing parameter. So you see here is 0 and here is 1. So you see that the curve here starts above 0, meaning that there is a chance of getting a little probability of getting the item right with very low ability. So this is guessing. Like, this is admitting that maybe like in multiple choice, if you guess, you maybe get some questions right. So this model admits this. The model, the 2 and 1 parameter model, this curve starts from 0, so not admitting guessing, right? There is another, the location of this curve, if it's to the right, it means that the item is very difficult because it needs a lot of it needs a higher ability to get a 1 on this item. And if it's to the left, it is an easy item. So the position of this curve that given by this point here, the point of inflection, right? And this number is the difficulty of the item that is in the same scale of the latent trait. So we have the latent ability and the difficulty of the item in the same scale. It's like a fight. If you have like two persons fighting, right? One side is the item developer, and the other side is the subject, the student trying to beat the item developer. And the item developer has a kind of constraint or a kind of a knowledge that he put on the item, and the person needs to like be above that to win this kind of challenge, right? So, and this is represented by the position of this curve. And then there's discrimination, is how this curve is the slope of this curve. Meaning that for a constant difference in theta, how much difference there is in these probabilities. So if it's higher, if it's a big difference, then the item is more discriminating. So you can see if this curve is very steep like this, it differentiates between below this difficult point and above. And if it's not, if it's increasing slowly, so it not discriminate too much. So enough of these 3. So are the 3 parameters. The thing here is just, so how the items are scored. That's the main question here. And the thing is that So here we have a representation. It's a very nice book explaining all the details of IRT. So each boxes here is an item. The green are the ones that the person got it right, and the red wrong. And they are positioned in the level of difficulty, like less easy and difficult, right? And then there is this location. This is the location of the person, like, and we want to know, we want to score, we want to position the person here, here, or here. What is the way that IRT scores is that it looks to this pattern of the response pattern of zeros and ones, and then try to find the theta that is most consistent with this response pattern, right? It's an interactive process that considers all the items and consider the information, like the difficulty, their discrimination, and the guessing parameter, and then tries to combine all this information to find the latent trait that is most consistent with this response pattern. So it's a kind of interactive process, right? For instance, in this case, the person is located here because below this level, he tends to get items right, and above this level, he tries to get the item wrong. And in the middle is kind of 50% chance, and that's disequilibrium, means that their latent trait is close to the level of difficulty of these items here. So that's why the position is here. So that's the way that the score is, the IRT score of these tests. So what is the practical application? How ENEM is scored? So I would ask you a question. For instance, if you have like this response pattern and this one, like these are items, 15 items, they are awarded by easy to difficult. And then we have like 5 out of 15 items. So this is 5 out of 15, 5 out of 15, 5 out of 15. So the very different patterns. So this subject is getting the easy items right, and this one is getting only the difficult items right. Using the classical scoring, the usual way, the way we know is, so both subjects will have the same score, right? They will have the same ability. But what happens if we use IRT? Will they have the same score, or do they have a different score, and why? So you will see it depends on the model, if it's 1, 2, and 3 parameter. So I don't know if you want to answer, or you know the answer already for this. So let's see some empirical data to see. So I'm analyzing here like 2015 ENEM, the max test. So it's 549,000 students, and they are like 4 or 5 now, 1,000 cities. So it's the one of the booklets, the yellow, I think blue and yellow test. So it's a random sample of the, I think it were 4 million. I don't remember exactly. And so it's a nice sample from this, from the pool. And so here's the distribution of so I computed the traditional sum score, right? So 0 to 44. So you see the distribution is very low, like the average is 10, 12. So you see that most of the students have a low ability, and they still have a symmetry on distribution. And so this is the traditional score. This is the IRT score. So it's estimated in 0 and 1, and then converted to this scale. I think it's 500 mean, and the 50 or 100 is standard deviation. So you see, this is the final IRT score. And now, so you see the relationship between the two. So this is the IRT score, and this is the original score, like the sum score. And so this graph, so you see, is not exactly the same. The correlation is 0.88. And there is a lot of variation in this region, below average. So the color here, what I did here, I computed the difficulty of each item of the name. And then I computed a variable that says the percentage of items of the difficult items that the student got right. So they have like, for instance, 15, 10, right? 10, the score. So it's ones in 10 items. How many items for this 10 are the most difficult items? So, and then I compute the percentage, like 100% or, and then so you see 0 is none of them are difficult items, and this color, lilas, I don't know we name in English, blue or lilas, it's 100%. So what is happening? So you see the green here, those that are getting the difficult items right are having lower scores. So it's kind of counterintuitive. I don't know if you think that, but, and those that are getting only the easy items right have the higher scores. And there's a big difference. So you see from 300 to 600. I will say later that this can cost their entrance to the university. And why is this happening, right? Why the ones that are getting the difficult items right, more difficult items right, are getting lower scores here? So this doesn't happen on the other side for people that have higher scores, but it only happen here in the lower scores. So you will see that this is because of the guessing parameter. So that's what I'm trying to do. So here's another way to see this. So I selected 20 subjects. So here I have all the 45 items ordered by difficulty. And then, so this is the percentage of right responses, and then the IRT parameter here. And here, so, and then you have the ones and zeros. So you see these students that get only the easy ones, easy items, right? So they get the 562, 577, and so forth. And those that get the difficult items, right? We have like 300, 330. So that's what's happening. Why is this happening? Why, right? So in order to understand this, I did these questions. So is there a way that we can obtain like weights for each item, that we can calculate a simple weighted sum of these items, mimicking what the IRT does, so we can see why is this happening? So is there a kind of a simple way to look to this scoring engine of IRT to understand why the way it is scoring? So there is this optimal scoring weights, is this formula here. So don't worry, so I will explain visually this formula. So the idea of this optimum scoring weight is exactly that. So I get a score for each item here, that if I use this score and multiply by each response, each one, right? And then sum this score, I get a score that's similar, exactly similar, is sufficient statistic for theta, so the IRT score. So, but you see that's a complex formula here, right? The thing here is that I told you that depending on the IRT model, you have different results here. So for one parameter model, the score becomes 1. So you score the test like a total score. So you just count the number of correct responses. That's sufficient statistic for one parameter model. For the 2 parameter model is the discrimination parameter. So each item will have a weight related to its discrimination, right? So if an item is more discriminating, more valid, theoretically will weight more than the other. And what about the 3 parameter model? That's the most difficult one to understand, because the formula says that you ask for this formula, give me the weight for, so I want to score the student. And then you see there's theta in this formula. So the formula then asks you, okay, what is the ability of the student? Give me his ability, then I will give you the weight. Then you say, what? I want the weight to calculate the ability. How can you ask me the ability? So it's kind of a counterintuitive, but the thing is that these weights depend on also the ability. And this is strange. In the calculation is an interaction process, and then as we go via these interactions, we find the ability, and then depending on the ability of the students, the weight will be higher or lower. And then, so one way to visualize this thing is to do exactly a simulation, what I did here. So I have a link with the code in R and then and this graph. So what I'm plotting here is this, the information here is the, so the ability, so you have the ability on this line. What I'm plotting here is the weights, okay? The weights for each item. And each line here is one item from the least difficult to the most difficult item. And then like the dark orange here is higher weight and the white is a low weight. What is happening? So for this item here, like 42, so you see for low ability students, it's almost no weight here, right? 0 weight. And then it only the weight is only, so only high ability students get this, a lot of weight for this item. So what you see here is for low ability students, the very difficult items count nothing. So if they get this item right, it will be multiplied by 0. And then he will not get any point from these items. And for high ability students, there is no this difference. So you see that the shading of these lines, it's related to discrimination. The more discrimination you have on the item, the more weight we give for each item. But in the lower level, so you see that for very high, so the only items that will count are those very low difficult items. Why is this happening? So just to compare, this is the 2-parameter model. So you see every item have some weight independent of ability, okay? And here no, so here is dependent on the ability. So the thing is, why is this happening? There is explanation, very interesting explanation that ENEM does about this, and they call this pedagogical coherence. What is this, right? So if a participant gets a difficult question right and an easier wrong, and the difficult questions use knowledge from a lower level, we can infer that this is there is no coherence in this response pattern. So the model then assumes that because he's getting like only some difficult items right and not the easy ones. If there is only one scale, like one dimension behind it, and there's a cumulative dimension, how this can happen, right? That you get a very difficult items right, and then you couldn't solve the easy ones. So the model then looking to this, it assumes is guessing, right? So the model will assume that this correct answers on the difficult items will be guessing, and then they will not score. They will not give any point to this. So, but this is a kind of they call pedagogical coherence. Like this, it's the same thing I showed. So only when you get the easy one, like for these 5 easy right, you get a higher score. But this idea. This depends on the assumption of essential unidimensionality. There is one dimension behind responses that is driving. That's the only cause of these responses, and then. If this is true, then we can interpret like that. That's probably guessing. But my question is, the validity question I pose here is, what is the evidence that the correlations between the items are explained by only one big factor? What is the evidence of essential unidimensionality then? What if there are group factors, right? For instance, think about algebra, geometry, combinatorics, probability. So all those topics become like, they are like all one thing, like one like hierarchical development thing. For if, think about, is there a standard fixed order that we need to learn those things? If we don't, we can't learn. Like if we need to do first algebra, then geometry, or then probability, or if we don't learn this, we will not learn probability. This will be equivalent of unidimensionality in the context of learning. So probably there is other factors, I don't know. But anyway, so that's my question. But let's do empirical analysis to see that. So what I did is like a Rasch principal component analysis. What is this? So we run like a 1-parameter model and estimate like the ability and the difficulty of these items. then we use those parameters to predict what would be the response, right? Because if it's only one dimension, so we have it in these parameters, like the level of the person, the difficulty of the item, are those, and those are the only two dimensions that predict what will happen, right? Everything unexpected from that is random error, right? So what we do is calculate these expected probabilities, and then we calculate the residuals, what is left after we predicted each response. So we have the expected, then we have the observed, we have the difference, and then calculate this residual. And if there is only one dimension, right? If there's only one causes of, or there's only one dimension that causes these responses, this residual will be random noise, right? But if there is kind of a second dimension, it will show us correlations between residuals across items. So what we do is a principal components, like a factor analysis, or it's not factor analysis, but it's a kind of analysis of the correlations between residuals across items, and try to find like factors that have a size that is above what simulation studies showed us that will be random noise. So that you have here kind of some benchmarks to like the Enge values of the second factor, 1.5 or 2. But the thing is, so I run this analysis to see, is there other dimensions beyond the first one? Because you see, when we predict the responses, we are using the first dimension. So the residuals is just like, is what is left after we control for the first dimension. So just a note, so this is in psychometrics, we have this causal inference problem, but it's much more complicated because we think that the latent trait is the causes of the response. So it's unobserved, and we can't randomize, cannot think. So we just infer that this is a latent cause of these responses. But anyway, closing the parentheses. And so here is the results we have. So these are the loadings of the items, and here's the difficulty of the items. And you see, there's no point in like interpreting the negative and positive here because it's unrotated. But the thing is that we have like a group of easy items that form one factor here, and like a group of difficult items that form a second factor, that can be a second factor. And for my calculations, the size of this component was above those that indicates a random noise. So this must be, perhaps it's something that's happening here as a secondary factor. When I look to those four items, most of them are about probability, about using probability to solve the questions. Here are the items, so you can have the slides later, so you see. And these are very difficult items, but use probability. And the thing is, what the second evidence of the second dimension is that those items that combine in this where the residuals are correlated, they have the same domain. They kind of asking the same kind of knowledge and reasoning. So what I did was to compute a score based only on those items of the second factor. And then here you have the correlation with the original score of an A based on 3 parameters and all the items. And the correlation of this second score is only 0.30 with this one. And you see why, because of this one. So these guys have like average score on this new factor. Actually, this factor is not that average, so it's the average is here. So they have a higher score on the second factor, but very low scores on the ENEM, because those items are very difficult, right? That compose this factor, and they are not getting any point for any. So the red ones are students that have 3 of those items correct, at least 3. It's kind of 1,500, I think, students here. Considering the amount of so this could be also random, of course, but I found it strange, like we have like at least 1,500 students that get all those 3 items right, okay? So conclusions. So we found evidence from the secondary factor. There is evidence against the assumption of essential unidimensionality.
Ricardo, can you go back 1 slide, please?
Yes.
So what does the blue line signify?
The blue is the regression of only those red guys here.
Okay, and what
Kind
does
of
it
a
mean?
negative, yeah, it's kind of a negative. If I consider only these red points, there's kind of a negative relationship, right? So the higher they are in the second factor, the lower they are in the IRT in this three parameter. Why? Because they are getting the difficult items, right? Right. So so if I consider everybody, it's 0.30, but if I consider only these guys, of course, it's negative. But this is just to illustrate, right?
Okay.
Um, so, um, so should one question I put for discussion: should we assume that low ability students' correct answer on these items is always guessing, right? Because what is the model is assuming is that if they get a difficult item right, it's guessing, and it's done. So I give a lower score for this item. So my question is, what if there is a different strategy correlated with fluid intelligence, for instance, and that is reasoning, that's not crystallized intelligence, that's responsible for the correct answer on those items. One day I was presenting this, and someone from ENEM came up with the idea that she remembered like one student explaining those items, that the one strategy, and was kind of a different way, not using like the traditional formulas, but he could get the correct responses using a different strategy. And also reasoning is also important. Maybe they can find and create on the spot a new way to solve those problems, perhaps, right? But because we use the three-parameter model, that's this is not that's what's happening. So they are not getting points for these correct answers. So they will get a very low scores. And as I said, this students with the same total score would have a different IRT score, and the difference would be like 500 to 300. And this could cost their entrance in the university, right? And so let's just go back and see this. So you see, sorry. So here, so what so you see that the most difference will be here in this region for low ability students. But you see distribution are, most of the students are here, like 10, 12, 15 scores, 14. So most of the mass of students are here, right? So most of the students are being impacted in a way by this way of scoring. And you have like, yes, so that's the problem. So it's affecting a lot of students. So one policy question I have, so in a high stakes like exam like an ENEM, should we ever not give points for a correct answer? Assuming that those students have guessed the item and say, no, you're not getting the score. SAT doesn't use three-parameter scoring. I tried to see and review this, and they use, I think, IRT for equating, but they equate the total score, but they don't use the parameter model. I asked some people from ETS, and so in part is because of this problem, but in part is very difficult to, in part is another reason it's very difficult to explain for the public, right? And this scoring scheme and how the scores are produced, and so they decide just to give every like same total score will have the same I think the same level. They only will adjust the difficulties between tests across years, but they will not like use IRT for like scoring. What is implications in terms of costs, right, for society? So if it is guessing, right, and we give points, we do give points. So we are telling the student have the ability, but the student doesn't have the ability. What is the cost, right? Or think about the opposite. What is if it isn't guessing and we don't give the points, right? Is the cost higher or no? For my first opinion is no. The second point is much higher, the cost, right? You don't give the opportunity, perhaps. If we use one or two parameters, then the model will give the points, right? So that's why I propose this, that we should change for 1-2 or 1-2 2PL model will not have this big change on the scores. Of course, there's limitations on the study, right? One thing is one thing that will be very interesting is follow up the students. So if we can identify it, I know that's difficult, but anyway, and understand what they are doing, right? To do like cog labs with the students on these problems to see if is this guessing, do they understand what they are doing or not? So if you see the patterns, what is happening, right? So they are like getting a lot of items right, but they are very difficult items. And what is happening, right? So is this guessing? Probably for some students it is, for some items maybe it is, but is that for everybody? And maybe use these assessments with this specific like probability and see if there is another way, strategy that's easier. And another way to study this is to use, so we can do this with the database for ENEM, like to estimate one parameter, 2 and 3, and see external validity, correlating the scores of an aim with external variables. Because if it is guessing, right, and the three parameter model is discounting those and kind of cleaning the scores, right? And then the scores should be more valid, predicting external criterion with three parameter model than with 2 and 1 that doesn't clean those guessing behaviors, right? So in a way, this should be more valid than the other two. The analysis I did, there's not a lot of difference between those three scores, but that's another way to see this. And then also there is a way to do a residual analysis of 2PL model. So this is more technical because probably those factors, the question is, are those factors that I found, the second factor, like a substantive factor related to ability, or are they like an artifact of the fact that I'm not modeling discrimination? Because all those items, difficult items, they have a very low discrimination because they are very difficult. Okay, so this is, and then so this is another check I will probably have to do before. For a paper, I will have to do this because probably someone will ask to do that. And so that's the limitations for this. But anyway, I think I go back for the first question is, should we ever not give points, right? That's, I think, the main point here is in a large scale like this one. And there is some discussion. So I found this paper that they discuss exactly that. That the adjustment of guessing has some implications for equity issues. And then so this is not new in the field. The problem is that when we read all this paper, it's very difficult to understand this scoring engine. That's why I am doing this work and write a paper about, because I want to like do very simple wins, like kind of visualizing what's happening, right? And hopefully I thought you could see it here, right? And then so that's for now. I think maybe we can stop for discussion and